Welcome to Engineers Mindset. Okay, so let's say we have a problem. A 75 millimeter diameter compound bar is connected by shrinking a circular brass brush onto the outside of a 50 millimeter diameter solid steel rod. If the compound bar is then subjected to an actual compressive load of 160 kilonewtons, question says determine the load carried by the steel rod and the brass brush and the compressive stress set up in each material. Take Young's modulus of steel as 210 giganewtons per meter square and Young's modulus of brass as 100 giganewtons per meter square. Okay, so the first thing is to first of all understand what the question is saying. It says a 75 millimeter compound bar is connected by shrinking a circular brass brush onto the outside diameter of also the outside of 15 millimeter diameter solid steel rod. So the first thing is that we have a compound bar. So this is a compound bar, and the diameter of the compound bar is given as 75 millimeter. Okay, and this compound bar is connected by shrinking a circular brass brush onto the outside of 50 millimeter diameter steel. So we have a 50 millimeter diameter steel. Okay. So this is what we have. So this is a steel bar. The diameter of this steel is actually 50 millimeter. Okay. Meanwhile, this is a compound bar itself, and the diameter of the compound bar is 75 millimeter. Now, we are saying the question is saying that a brass brush is shrunk into the rod. So we have a brass brush actually shrunk into the rod, circular brass brush. Okay, so let's say we have an opening here, something like this, something of this nature. Alright, so we have a brass brush that actually shrunk into the steel bar. Alright, the first thing is that we have the steel and we have the compound bar. The compound bar is then subjected to an axial compressive load of 160 kilonewtons. So there's a load carried by this compound bar. The load is simply 160 kilonewtons compressive. Okay, so this can be called a brass. Okay, so you have this. Now the first thing to do is to find the area of the compound bar. Area of the compound bar. Okay, so notice that the steel bar is actually inside the compound bar. So which means the compound bar is actually in a double hollow section. It means the compound bar is actually a double hollow section. Therefore, area of the compound bar, and use area C to represent compound bar, is actually pi over 4 times the external diameter squared minus internal diameter squared. We have this capital D stands for the external diameter of the compound bar itself, while the smaller distance for the internal diameter of the steel. So we have two diameters here, 75 millimeter and 50 millimeter. 75 is the external diameter, which is the larger diameter, while 50 millimeter is the internal diameter, which is smaller diameter. Okay, so D, or external diameter, okay, which is actually G, is 70 millimeters. So we convert this to meters. So that will give, 75 millimeter. Convert this to meters. That simply means that the external diameter is actually 0. Divide by 1000 to give us 0.123, 0.75. Please check. 0.075. 0.075 meters. Okay. Meanwhile, the internal diameter is smaller d. Internal diameter is smaller d and is given as 50 millimeter. So converting to meters, you divide by 1000, you have t to be equal to 0.05 millimeters. So if you have this, then the area of the compound bar, which is AC, is simply pi is given as 8.142, it's a constant. So pi is 8.142 divided by 4 times the external diameter is 0.075. So you have 0.075 all squared minus the internal diameter, which is 0.05. So you have 0.05 all squared. Okay, so you have this. So area is now equal to, please, 3.14 divided by 4.
0.78.
0.78.
7855.
0.78 what?
55.
55 multiplied by 0.075 squared is what?
5.625 times 10 to the power minus 3. 5.63 times 10 to the power
5.65 10 to the power minus 3.
63
Okay, 63
times 3 to the power minus 3.
by 10 to the power minus 3 minus 0.05
2.5 times 10 to the power minus 3.
minus 3. Okay, so evaluate the number of this. What do you have?
2.46.
So area of the column is 2.46 by 10 to the power minus 3. So this is all the area of the compound bar itself. Now, but the steel and the brass brush is actually inside the compound bar. So, okay, we'll go to the area of this compound bar. Let's now find the area of the steel. The steel diameter is given as 50 millimeter. So we can obtain the area of the steel. So we can call that AX, and that's simply pi over 4 times diameter of steel all squared. That's equal to pi is 3.142 divided by 4 times diameter of steel is given as 0.0505 all squared. So area of steel is equal to 3.142 divided by 4 is 0.7855 times diameter square 0.05 square is 225 by 10 to the power of minus 3. So what is the value for this area? Multiply to what you have.
We have 1.96.
1.96 by 10 to the power of minus 3 meter square. Okay, now take note. The steel bar and the brush bar is actually inside of the compound bar itself. So it means now that the total area of the compound bar is equal to the area of the steel bar plus area of the brush itself. So area of the compound bar, that's AC, is simply area of steel plus the area of the brass itself. But we know the area of the compound bar, it was given very subital to be 2.46. So we have 2.46 by 10 to the power of minus 3, and that's equal to area of steel was given and result as 1.96 by 10 to the power of minus 3 plus area of brush. So we make now the area of brush, so to the formula. Simply send 1.96 by 10 to the minus 3 over to this side. If this positive sign constant equal to sign, it becomes negative. So therefore, the area of the brush is now equal to 2.46 by 10 to the power of minus 3 minus 1.96 by 10 to the power of minus 3. Okay, so that will give us the area of the brush or the brass. So AB, area of the brass brush, is simply equal to 5 by 10 to the power of minus 4 meters squared. So now the area of the brass. Minus 3. Minus 4. So that's the area of the brass brush. Now, if you've not watched the first video on introduction of stress reducing compound bars, please do well to go and watch it, because I took my time to explain the basic equations we need to analyze stress reducing compound bars. The very first equation we need is what is called the compatibility equation. So from compatibility equation, we simply said that the strain of a steel rod must be equal to the strain of the brass rod. Okay, strain of one material must be equal to the strain of the other material for compatibility to be achieved. And recall that strain itself is simply stress divided by Young's rules. So if strain simply means stress over Young's rules, it means now that the stress of the steel rod is not going to be the strain of the steel rod is not going to be the stress of the steel rod all over the Young's rules of the steel rod, and that's equal to, meanwhile, the strain of the brass rod or brass brush is going to be the stress of the brass brush all over Young's rules of the brass. And from the question, the Young's unit of steel was given as 100 giganewtons per meter, sorry, 210 giganewtons per meter square, while Young's unit of brass was given as 100 giganewtons per meter square. So we can simply have this to be the stress of steel all over, in place of Young's unit of steel, we are given as 210 by 10 raised to the power 9, and that's equal to stress of brass all over. The Young's unit of brass was given as 100 by 10 to the power of 9. So you have this. So at this point, this is what we do. We want to let's make stress of steel bar subject of the formula. So we simply cross multiply and send this man, the Young's unit, over to this side of the equation. So let this Young's unit multiply this side. So we are simply going to have that the stress of steel, okay, is now equal to 210 by 10 to the power of 9 multiplied by the stress of brass all over the Young's unit of brass, which is 100 by 10 raised to the power 9. Of course, 210 by 10 raised to the power 9 divided by 100 by 10 raised to the power 9 will simply give us that the stress of the steel bar is simply 2.1 stress of the brass. So call this equation 1. So this is the first equation to be considered, the compatibility equation. The next equation to be considered is what is called the load equation. Now, what is the load equation? The load equation simply says that the load carried by the compound bar is equal to the sum of the individual load carried by the materials that makes up the compound bar. Okay, so what that means is this: load carried by the compound bar P is simply the load carried by the steel rod plus the load carried by the brass rod. Okay, so that simply will give us now. But recall that stress itself is simply force or load all over area. So that simply means now that if we make load solve the formula, it's going to give us stress times area. So the load or the force is simply stress times area. Therefore, the load carried by the compound bar P is simply the load of steel bar can be likened as stress of steel bar times the area of steel bar. So this will give us stress of steel bar times the area of steel bar in place of PS, plus in place of PB we are going to have stress of the brass rod times the area of the brass rod. So this will give us total load carried by steel bar. Meanwhile, total load was given in the equation carried by the compound bar as was 160 kilonewtons. So you're going to have in place of total load is P 160 kilonewtons times 10 to the power of 3, and that's equal to stress of steel bar times area of steel bar plus stress of brass times area of brass. But recall from equation 1, from 1, we have that stress of steel, sigma x, is simply 2.1 stress of brass. So in place of stress of steel, we simply put what? 2.1 stress of brass in place of stress of steel. So that simply means now that 160 by 10 to the power of 3 is now equal to, in place of stress of steel, we simply have 2.1 stress of brass times area of steel, which is this AX, plus the stress of brass times area of brass. That's the first thing we do. Next, recall, or we've already had the areas. Okay, recall that we've already found the areas. Area of steel bar was given as this, which is 1.96 by 10 to the power minus 3, while the area of the brass was given as this, which is 5 by 10 to the power minus 4. Okay, so we simply substitute that into the equation. So we have that 160 by 10 to the power of 3 is now equal to, this is 2.1 times stress of brass times area of steel is given as 1.96 by 10 to the power of minus 3 plus stress of brass sigma b times area of brass is given as 5 by 10 to the power of minus 4. So you have this. So at this point you have 160 by 10 to the power of 3 is now equal to 2.1 times 1.96 by 10 to the power minus 3. What do you have? 2.1 times 1.96 by 10 to the power minus 3.
0.116 times 10 to the power minus 3.
4.116 by 10 minus 3 sigma d plus 10 to the power minus 4 sigma p. So of course these two can add because this sigma brass, stress of brass, and this stress of brass, so they can add. So 4.116 by 10 to the minus 3 plus 5 by 10 to the minus 4. So add them together, what do you have?
4.616
4.616
times 10 to the minus 3.
minus 3 sigma brass. So we can make the stress of brass subject of the formula. So that simply means that stress of brass is equal to divide by 4.616. So you have 160 by 10 to the power of 3 divides 4.616 by 10 to the power of minus 3. What do you have? We give a very good value. Sigma b is equal to
34662
045.06 newtons per meter square. So you can choose the one to approximate 1, 2, 3, 4, 5, 6. So that simply means you can as well also say sigma b, or the stress reduced in the brass, or the simply 34.66. That's mega newtons per meter square. So you can go with this, you can as well go with this. That's the first answer. That is the first stress reduced in the brass rod. The next, to find the stress reduced in the steel rod. Recall from equation 1 here. Recall from 1, we said that stress reduced in the steel rod, sigma x, is actually 2.1 stress of the brass rod. So that means stress of the steel rod is now 2.1 times stress of the brass rod was 34.66 meganewtons. So let's use this 34.66. So that implies that stress reduced in the steel meganewtons. Multiply by 2.1.
72790.296.
This is equal to 7279. Use this.
Okay.
Use this. 2.1 by 34.66.
72.786.
So 72.78 meganewtons per meter square. So that is stress reduced in a steel rod. What other question was asked? Alright, so these two stresses, sigma b and sigma x, are actually the compressive stresses carried by each of the material. The next question is to find the load carried. Okay, to obtain the load of steel, okay, we simply say load is simply stress of steel times area of steel. So load of steel is equal to the stress of steel was obtained at 72.78 meganewtons. So this is 72.78 by 10 raised to the 6 is mega times the area of steel. Area of steel was given as 1.96. Okay, we solve it as 1.96 by 10 to the power of minus 3. So this is the load carried by the steel. So please multiply all for me.
142648.8.
142648.8 newtons. So this is load carried by the steel. So you can choose to approximate 1, 2, 3. So that simply means that load carried by steel can be 142.65 kilonewtons. If you wish, you can leave it like this. You can actually leave it like this as the answer. That's the load carried by the steel. While load carried by brass, load carried by brass, that's PE, is simply the stress of brass times the area of brass. So the load carried by brass is equal to stress of brass was given as 34.66 meganewtons. So you have 34.66 mega means times 10 to the power 6. Okay, times area of brass. We got area of brass as 5 times 10 to the power minus 4. So what is the load carried by brass? Give me now multiple.
51,232.77.
51,232.77 units. So you can also choose to approximate 1, 2, 3. So you have that load carried by grass PE is actually 51.23 kilo units. So you can call this your answer. You can also call this your answer. That's it, guys. I will see you in the next video with another wonderful question on compound stresses. In the meantime, if you're new to the channel, don't forget to subscribe and of course like, share and comment. I would like to hear your thoughts in the comment section. Thanks and cheers.